All right. So the other day we were talking about gravitation. So let me kind of jump ahead to where we were at. So we kind of ended with the shell theorem, and I did kind of a rotten job explaining that. I overcomplicated it, I think, more than we needed to. Here's what the shell theorem boils down to. We calculated force of gravity, depending on where you were at on the Earth. All right, so here's the deal. All right, let's imagine several imaginary, that was a redundant sentence, Earths, okay? So imagine one Earth that is a point particle with a mass of 5.98 times 10 to the 24th kilograms, all right? I'm sorry? Yes, it would. There would be some issues here. But just for simplicity, point particle, and then here's you floating around at a distance of the Earth's radius. So I'm just going to call that RE. Cool? All right, so that's imaginary Earth number one. All right, here is imaginary Earth. Oh, that's not what I wanted to happen. Here is imaginary Earth number two. It is a hollow shell with a radius equal to the Earth's radius and a mass equal to the Earth's mass, and you're standing on it. All right, and then here's the actual Earth. All right, in all three of those circumstances, your weight due to the Earth's gravity would be the same. That's what I did a crappy job of explaining the other day. Does that make sense? Yep. So whether you've got, basically what it boils down to, as long as you're, oh, I guess I shouldn't say that because it's not true if the object isn't spherical. So if you've got a point mass of 5.98 times 10 to the 24th kilograms, the Earth's mass, and you are a distance of one Earth radius away from it, then the force of gravitational attraction between you would be the same as it is for the real Earth. Cool? In other words, we can treat this Earth as being a point particle located at the Earth's center. Cool? And similarly, if it's hollow, that doesn't change anything, as long as the mass and radius are unchanged.
That's assuming that the Earth is perfect sphere.
Yes. Yes. Yeah, Ethan.
You're inside the house, yours are...
Okay, and so the last part of the shell theorem, I don't remember if I talked about it the other day, but if you're, oh yeah, we did. If you're inside the shell, then what? Do you remember?
No.
Yeah, then your net force is zero. All right? So let me move all this stuff out of the way. All right, and then so then the final one is if the Earth was a hollow shell and you were anywhere inside it, then the force of gravity from the Earth's attraction would have a net sum of zero. Please hear me say this. I'm not saying that there's no gravity in here. What I am saying is that the force of attraction pulling you up from the mass above you is canceled out by the force of attraction of the mass below you. Because even though the mass below you is farther away, there's more of it. Good? Yes.
So, like, if you were to fall through one of these,
That's where we're headed. So hold that thought for 1 second. That's honestly right. That's going to be the next thing. But I want to make sure everybody's good with this before we move on. Everybody good? All right, cool. So let's go back to solid Earth. Suppose you dug a tunnel down through the middle and you were partway through the tunnel. Okay, so we're going to start there and then we'll talk about what happens if you fall all the way through. Is that sort of where you were headed?
yes.
Is that okay? Okay, and if I don't answer your question, then
I
ask.
will have to.
Okay, all right, so here's the Earth, right, with a tunnel dug through the middle, all right? Let's do this. So here's the Earth. Here's you. Hello. Okay? Now remember that you can kind of treat the Earth as this, you think about the solid Earth, you can treat it as a collection of shells, right? There's a shell, outside of a shell, or inside a shell, inside a shell, inside a shell, right? All the way out, right? Good? And then just add up the effects of all of those shells. Now, if you're inside the Earth, there are going to be some shells that you're outside of and some shells that you're inside of, right? Does that make sense? So, what's going to be the net effect of everything outside the dotted line? 0, right? Because if you think of that as being a shell and you're inside it, then the force of gravity by everything out here is going to cancel out to 0, right? Does that make sense? So really, what it boils down to is what the book calls MINS, as in the mass of the remaining mass of the Earth that's inside the shell that you're sort of occupying. Does that make some sense? All right. So for simplicity, and this is a giant oversimplification, otherwise it gets really complicated. If you assume that the mass of the Earth is evenly distributed, it gives a really easy result. Okay. So, do you want me to derive that result, or do you want me to just tell you the result? I'm okay with either answer. Derive it? Okay. So, here's what I want to do then. So, we're going to shrink this. Oops. Okay, so our force of gravity, the force of gravitational attraction here, is going to be equal to G times little m, that's usually assumed to be the mass of the smaller object, times, now remember, all I really care about is the mass inside that circle, right? Because everything outside the circle cancels out, right? Okay, and then how far am I from the inside of that circle? Well, let's call this r, as in the radius of the Earth, and then we'll call this the radius of the shell little r. Cool? So that's just r squared, right? Make sense? All right. So basically what we need to do is, we can pretty safely assume you know r, right? It's like, well, how deep is the hole, right? And then you can find r, right? But what we don't know is the mass of the Earth that's inside that shell. Cool? So here's what I'm going to do. I know, because I took some math class at some point in my life, that the volume of a sphere is 4/3 pi capital R cubed, right? Good? And I know that the volume of the sphere inside is 4/3 pi little r cubed, right? Does that make sense? All right, now, if I assume uniform density, shouldn't those volumes be proportional to the mass? Does that make sense? Okay, so what that means is that the mass inside the shell over the mass of the Earth ought to be equal to the volume inside the shell over the volume of the Earth, right? Which is just this over that, and it gives you r cubed over r cubed, right? Follow? Question?
I was just saying, in the homework it said uniform density, so it's density.
Say that one more time.
It said uniform density.
Right.
Well, I guess.
Yeah, uniform density means that the density of any chunk is the same. So density is mass per unit volume, right? So you can take any chunk. You could do the whole Earth and the whole Earth, or you could do just that inside chunk over the volume of the inside chunk, and then what, cross multiplying, or what, rearrange it gives you this, right? Is that what you're saying? Are we saying the same thing? Okay, everybody good? Okay. All right, so, oops. So where do I want to go then? Oh, okay, got it, sorry. Somehow I misplaced my notes from last Friday, so I'm doing this from scratch here. I didn't have time to do these before, during my 5th hour, because that's often people during my 2nd hour. All right, so if I multiply both of this by mass of Earth, then I get this. Mass inside equals r cubed over r cubed times mass of Earth. Oops, mass of Earth. Follow? So all I'm going to do is I'm going to substitute this mess in here. Any problems? All right, and you get a kind of a satisfying result. I mean, you know, as much as can be expected with, you know, giant equations like this. So you get this, Fg equals G times M times, let's see, R cubed ME over R squared times R cubed, right? Follow? So let's see, R squared and cubed cancel, so you're just left with an R on the top, right? So look what you get. You get G times M times ME over, I'm going to cheat, R squared times R, oops, over RE. In other words, it's the same as what you would weigh at the surface of the Earth times the ratio of the Earth's radius to your radius. Make sense? Which makes sense because if R is 0, in other words, if you're at the center of the Earth, what are you going to weigh? Nothing, right? Because you're going to have equal force pulling you in every direction, right? And if you're at the Earth's surface, then R becomes capital R, and this is all just 1, right? Make sense? So, if you are in a hole in the Earth, some distance down in the Earth, your weight is equal to the weight at the surface times this ratio. The distance you are from the center of the Earth to the radius of the Earth itself. Cool? The way the book writes this, let me say one last thing and then I'll get your question. The book writes this way. Which to me isn't quite as intuitive. It's the same thing, but for whatever reason, this just feels easier to remember to me. So however you want to think of it. Alex. No. Well, no. Because then that would be saying that you weigh more as you get farther away from the Earth, and that's not true. Follow? So what do you do if you're farther away from the Earth? Then you just use the FG equation, right? Where R would be the distance you are away from the center of the Earth. Follow?
Yeah.
So radius of the Earth plus how far you are above it, if you want to think of it that way. Cool? All right. Questions on all of that? All right. So here's the neat thing. Notice. You guys remember Hooke's law, right? F equals kx, right? Where x is the displacement you are from your sort of equilibrium point, right? Check it out. If I'm at the center of the Earth, wouldn't my r be 0? Right? Doesn't this thing stay constant? Isn't that a fixed value? Right? So if I think of this as k, and I drill a hole through the Earth and jump through it, it's exactly a spring. Here's my spring constant times r. Right? Because this value is fixed, right? And a radius of 0 is equivalent to having your spring unstretched. Did I say that right? Spring unstretched. Make sense? So, let's jump ahead and take a look at the next slide here. Make sure I hit everything. I think we did. All right, so shell theorem, we talked about that. So this first chunk here, let me kind of review here and make sure that everything all fits together. All right, so this first chunk here basically just says that as long as you're outside of the Earth, you can treat it as a point particle and just measure the distance you are away from that center and use the gravitation equation, this guy. Or, well, yeah. Good? The second part of the shell theorem says that if you're inside a shell, the sum of the forces is 0. Cool? And then this is that equation that we just derived. No, it isn't. This is that equation we just derived. But we started with this. Cool? All right, and then what I was saying is, if we think of this thing here as a constant, if I think of this thing here as a constant, then this basically becomes so fluff. So F equals negative k times r. The negative is just telling you opposite direction, right? So that if I'm here, then my radius is positive, but my force is negative, right? And down here, my radius is negative, but my force is positive. Yeah, anywhere other than in the middle, yeah. That's the point.
It's not hollow.
It's not a shell, this is the hole through the center of the Earth.
Oh.
Cool? Also, probably worth commenting on, we're assuming that the mass we lose due to the hole is negligible, right? Very, yeah, so a very skinny hole.
So let's say there's the land inside of the sphere. Technically, they just get floated around.
Yeah.
Well, it would depend on how the mystical land worked. If it was a tunnel that went all the way around like this, then no, they would just weigh less. But if it was like this, and they were in there, then yes, everybody would just be floating around. All right, so are we good? All right.
That would take a big drill.
It would take a big drill. All right, any questions on all this? All right. I'm debating adding in an example that's not in the notes that I think is probably worth doing.
Yeah, why not?
You guys want to find out what your velocity would be if you jumped through the hole?
Yes.
I kind of feel like we should figure that out. Don't you think? All right, let's do it. I've never done this before. Are you ready? All right, so here's the Earth. Hole. Here's you. Boop. You're going to drop through the hole. I don't think it should matter. Let's make up a number just in case. Like I said, I've never done this before. Let's find out. We'll go through and we'll do it, and we'll see if it works. All right, so here we go. Mass of U. Let's use 100 kilograms. Radius of the Earth, which I'm from this point forward just going to call capital R, is 6.38 times 10 to the 6th meters. Mass of the Earth, which from this point forward I'm just going to call capital M, is 5.98 times 10 to the 24th kilograms. We're going to call your position at some point, we're going to call that R. Cool? And so what we just discovered was this, that the force on you at a radius as a function of R is G times your mass times the Earth's mass times capital R squared times R over R, right? Okay, and then we're going to rewrite this as G times M over R cubed times R, and we're going to call this whole mess K. Follow? All right, so that means that F of R is, let's figure out what K is. That is going to require the use of a calculatrix. So let's see, G is 6.67 times 10 to the negative 11 times your mass is 100 kilograms times the Earth mass is 5.98 times 10 to the 24th kilograms divided by the Earth's radius cubed, 6.38 times 10 to the 6th cubed gives us 1.536, we'll call it, times 10 to the negative 4th, and that ought to be newtons per meter, right? It's supposed to be like a spring constant, right? Oops. Did I type something in wrong?
Divided by 6.38 times 10 to the 18. Yeah, that's what I did.
Times 10 to the 18th?
Right, it's 6 raised to the third power.
But you got to cube the 6.38 also.
Right. So when you raise the next one,
you got to do 6.38 cubed times 10 to the 18th.
If you're like xy cubed, it's x cubed, y cubed.
So if you divide that by 6.38 two more times, you ought to be good. Did that work? Okay, cool. Thank you for checking me, because like I said, I haven't done this. I was going to do it 5th hour, but I was helping some people with stuff. And screwing around, to be honest. But anyway. All right, so is everybody good up to there? All right, so check it out. So if we think of this as a spring, this is like elastic potential energy, right? And what's the equation for elastic potential energy? 1/2 kx squared. Oh, and here's my k, right? And here's my x. Follow? Then, as I fall, I lose elastic potential energy, but gain kinetic energy. What's the elastic potential energy in the middle? 0. And therefore, my kinetic energy at that point ought to be equal to this number again, right? Follow? And I think that I could have left m out of this and everything would have worked, right? Because this depends on m. And at the other end, 1/2 mv squared depends on m. So those m's would have canceled. So our answer is the same regardless of mass. Okay? So we are almost done here. So our gravitational potential energy, and this is a little sloppy because we're kind of cheating using the result that we got for springs and just making a parallel, is going to be 1/2 kx squared as you are descending through the earth, right? So that's 1/2 times 1.536 times 10 to the -4 times, what do I use? Use the radius of the earth, right? So 6.38 times 10 to the 6th meters squared. So I guess I should put a little O here, right? Because that's the gravitational potential energy you begin with, right? Follow? All right, and then that's going to equal 1/2 of your mass, 100 kilograms, times v squared, and solve it. Good? The 1/2s cancel out, which is a nice little bonus. And let's see what we get. Somewhere I have a calculator. All right, let's see. So there's my k. I'm going to multiply that by the radius of the earth. Squared divided by 100. Square root of 5. 7,907 meters per second with a complete disregard of significant figures.
That'd be your velocity.
So that would be your velocity at the center of the earth. Then what's going to happen? Then you're going to slow down, right?
The air, then you're going to be stuck.
But it's going to be weird because pressure isn't dependent on your vertical position and you're no longer at 1 atmosphere.
Yeah.
Things that happen if you fill the hole. So,
Plus you can.
Yeah, plus for the earth being molten lava.
yeah.
All right.
So there's some issues. All right, anyway, does this make sense, guys? I've seen this question somewhere. I don't remember if it was on a homework assignment or an AP test or something, but I've seen that somewhere. That's the first time I've actually done it. All right, does it make sense? All right, cool. So that is force of gravity. All right. So at this point, I guess I would expect you to have 3 big takeaways, maybe 4. Big takeaway number 1: if you're outside the mass, then you basically treat it as a point particle, as long as it's a sphere. Okay. We'll deal with non-spheres later if this time. If you're inside the shell, then your net gravitational force is 0. If you are inside a solid sphere, then you got to do this thing with the ratios of the radii. Good? And very specific takeaway: if you dig a tunnel through the earth, then you can treat gravity like a spring. Cool? Questions? All right, cool. All right, gravitational potential energy. Oh, wait, try that again. Energy. All right, this, I'm going to be honest, I wish I could say this was awesome and it was super cool, but for whatever reason, dealing with gravitational potential energy in this sense is a drag. All right, we can't just use MGH anymore. Any ideas why? What assumption does MGH make? That G is 9.8 meters a second squared, right? Which is only true really at one very specific radius from the Earth's center, right? Now usually it's pretty close to 9.8, so we can kind of look the other way and go, oh, close enough, right? Because within sig figs it doesn't matter. All right, but now if we're talking about, you know, being in the space shuttle, some huge distance away from the Earth's center, now your acceleration is no longer 9.8. It's, you know, whatever it is, right? So it becomes problemsome, not a real word. All right, so how do we deal with that? All right, so here's the deal. So technically speaking, all of those times that we found the gravitational potential energy, like so if I stand on the table and we go, oh, Mr. Hecker has gravitational potential energy of whatever, MGH, technically that's not my gravitational potential energy. It's the gravitational potential energy of me and the Earth. Okay? The Earth is pulling me down and I'm pulling the Earth up. Okay? And there isn't really a way to figure out how much of that energy is mine and how much of it is the Earth's. Follow? But what I do know is that when we release it, I'm the one that's going to get most of the kinetic energy because I have a smaller mass, right? In other words, I'm going to accelerate way more than the Earth does, right? Follow? All right? But technically speaking, the Earth sort of shares that energy with me. Just it turns out that it has a much sort of smaller percentage of it. Okay? So that's kind of what this is about. It says no gravitational potential energy is a property of a pair of particles. In that case, me and the Earth. And we can't really say how much of the energy is mine and how much is the Earth's. All right? So, you know, in that example, like if I hold a baseball up and we talk about the GPE of the baseball, technically that's the GPE of the baseball and the Earth system. Okay? Yeah, and this is what I just said, right? Yeah, so we can get away with this because the energy change is almost all kinetic energy of the smaller object, me or the ball or whatever. Now, notice that only works because in both of those examples, whether you're talking about me or a baseball, me and the baseball are both significantly less massive than the Earth, right? Now, when you're dealing with objects that have comparable masses, or remotely comparable, then it gets more complicated. All right, and so it turns out that this is the equation that you use to calculate the gravitational potential energy between two masses. All right, now here, capital M and lowercase m sort of lose their meaning, right? Because you might have two objects that have the same mass. You know what I mean? So, to be honest, I used to write this as M1 and M2. But whatever, okay? The point is there are two masses being attracted by a mutual gravitational force, and that results in gravitational potential energy. All right? Have you guys seen this equation before?
Yes. Absolutely.
Okay.
No one remembers it because it was a take-home test.
I got it. Right. Okay. Understood. All right. Okay. That's all right. All right. So here's why it's weird. And even now, every time I do this, I go, oh, I got to stop and think about this. All right? So what this means is this. As my radius increases, well, first of all, notice the negative sign. Okay? So from this point forward, when we use this equation, gravitational potential energy is a negative value. I know, I do the same thing. Patrick's gonna go, what? All right? So look, let me insert a blank page here. All right, so here's the equation. Gravitational potential energy is G times capital M times little m over R, stupid negative sign. All right? So, hypothetically, here's our point particle Earth, M. Okay? Now, what? So, and then let's just do this. Let's do little m here. And here's our R, right? Now, what happens to this value as R gets bigger and bigger and bigger and bigger and bigger and bigger and bigger? It goes to 0, right? In other words, the limit as r goes to 0 of u is, oh no, as r goes to infinity, sorry, is 0, right?
Yes.
In other words, as this gets bigger and bigger and bigger and bigger, my ratio gets smaller and smaller and smaller, okay? So potential energy is defined to be 0 when things are infinitely far apart. Cool? Now, when they get closer and closer together, as r gets smaller and smaller, this value gets bigger, but more negative, right? Does that make sense? Okay? So, the limit as r goes to 0 of u is actually negative infinity. But is it possible to have two objects that are a distance of 0 units apart? No, right? Because otherwise they wouldn't, right? You can't have particles with mass that don't take up some space, right? So your distance is never going to get to 0, right? But the point is, if you put them super, 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 super close together, that's like saying that they have a infinitely negative potential energy, or close to infinite. Follow? All right, so here's all you really need to know. Look, if I take this remote control and forget about this for a minute. If I lift it, what did I just do to the gravitational potential energy? Increased it, right? The same is still true, okay? So I'm going to just make up some garbage numbers for a minute, just to show you what's going on. All right, so let's suppose that this object right here has a gravitational potential energy of, whatever, negative 20. I'm not even going to worry about units. All right? And then I lift it up to here. Oops. New r prime we'll call it. So my gravitational potential energy should be a bigger or smaller number than 20? A smaller number than 20, right? So maybe it's 10, who cares? But still negative. So going from negative 20 to negative 10, is that an increase or a decrease? It's still an increase. Okay? So long story short, the farther two particles are apart, the more potential energy they have. If you remember that, you're in good shape. And then try not to get too bogged down with the negatives. Okay? Past that, I would say just kind of trust the equations. Okay? So here, oh, I wanted that to be a different color. Horrible. You increase just as expected. Good. It's that it's getting less negative. When you lift something, the GPE gets less negative. Cool? Yeah, it is.
So it's like the same idea as like having, you say like there's like more gravitational potential energy, just MGH be moving higher, because it's higher, it's like the same thing, but less negative, but still.
Exactly. Exactly.
The gravitational potential energy increases, but the force between particles decreases.
Correct. Which that's true here too, right? Because the farther something is away from the Earth, the less gravity pulls it down, right? But it's still higher up, so it still has the potential to gain more kinetic energy as it returns back to the Earth's surface. Follow? The only difference is, as it falls, the force gets bigger, so the acceleration gets bigger, but even way up here, with a smaller force, it's still going to accelerate, just not as quick, you know? Cool? All right. So, that is the deal with potential energy. I think the big things to say, let me say this one last thing, Patrick, and then I'll get you. I'll get your question. I'll get you. All right, so I guess we already illustrated this, but note that your potential energy is always going to be negative, and as your R gets bigger and bigger and bigger, it gets closer and closer to 0, which technically is increasing, right? Because the smallest negative number you can have is 0. That's terrible, because 0 is not negative, but the smallest non-negative, or non-positive number you can have is 0. Or biggest, please. Anyway, you know what I mean. Yes? it's just a quantity. It's like, I mean, let's suppose that you and I crashed on a desert island and we both had a debt of $1,000. As long as we're on that island, our debt's going to stay at negative $1,000. You know what I mean? So the fact that it's negative doesn't change it. It's still, it's just a way of quantizing it. It's a way of counting sort of how much we've got. I know, it's weird.
It's like drawing a zero where anything, like, it doesn't matter where you place your origin.
Yeah. Sorry, Carson, you sort of... All right. So yeah, I mean, I guess if you want, hey guys, what Kurt just said is really insightful. So usually when we've solved problems, I know I said this a billion times in my honors class, maybe not as much with you guys, but like if you're just doing a regular old conservation of energy problem with gravitational potential energy, usually I tell you, find the lowest point in the problem and call that a height of 0, right? Good. And then everything becomes a positive height from there, right? This time we're flipping it. Now we're taking the highest possible point, calling that a height of 0, and calling everything else a negative height. For reasons that we'll maybe talk about tomorrow when we get deeper into this, but keep chugging away. Right now you've done everything you need for the first chunk of the 13 assignments, so be working on that. We'll find a day to go over it here.
I'm sorry, I still
Yes.
had this card.